Hello, everyone. I'm going to do a quick little intro to Hess's Law. This is definitely a new idea that you haven't seen in chemistry before, but we'll be applying it in many ways throughout the semester, not just with delta H, but with delta G and delta S. It can be used in many different ways. And it's a way to combine different reactions to get to the reaction that you want. So I want to show you and kind of introduce to you how this works, and then you will be able to practice it yourself. So the gist of it is you have multiple equations that can get you to a different equation. So going from a particular set of reactants to a particular set of products, change of enthalpy is the same whether reaction takes place in one step or a series of steps. That makes it a state function. Delta H is a state function just in this example, because it doesn't matter how many steps you go to as long as you're going from certain reactants, certain products. So what is meant by that? Well, here is nitrogen and oxygen getting together to make nitrogen dioxide, and the delta H for that reaction is 68 kilojoules. But as we'll see later when we get to kinetics, these reactions don't always happen in one step. And in a lot of cases, you can't make them happen in one step depending on the reaction you have. But you could have possibly information about the different steps it takes to get there. For instance, if I know the information about this reaction, nitrogen plus oxygen making nitrogen monoxide, and that the delta H is 180, and then that nitrogen monoxide reacts with more of the oxygen to make nitrogen dioxide, and delta H is negative 112, for that reaction, I can add those two reactions together. And notice what happens is that the nitrogen is still here. The nitrogen monoxides cancel out. If one's on a product side and one's on the reactant side, for the two reactions, they cancel out. There's two of the oxygens, so that's why there's a 2 here. And there's 2 NO2. So we've got our reaction up here, and look at what happens when we add those two delta H's together. We get that 68 kilojoules. So regardless of if it's a one step or if you're doing multiple reactions to get the same reaction, the kilojoules or the heat of the reaction or the enthalpy of the reaction will be the same regardless. So some cases it could be given to us, but in some cases we may have to use multiple reactions to get to the one that we want. I'll show you what I mean by how we would approach that. This is just another way of looking at it. So this reaction, if we look at the H here, or the energy involved, there's energy going into this first reaction to go from N2 and O2 to still have O2, but to some nitrogen monoxide, so energy's in, so that's why it's mean endothermic. This process is exothermic, but overall, since there's more in than out, that's why it'd be 68. And again, here's the one-step reaction, but the same number regardless of the method that you do it. So here's a couple of rules as far as enthalpy changes go. If you have to reverse a reaction, then the delta H would be reversed, and I'll show you what that looks like. The magnitude is directly proportional to the quantities of reactants, kind of how you saw in the stoichiometry. So if we double the reaction, we'd have to double the delta H. If we cut the reaction in half, we'd have to cut the delta H in half. And again, I'll show you what that looks like. So we want to try to get to this reaction right here. That's the example that we're trying to get. We want to get to this reaction. But these are the two reactions that we have. So how can we get to this reaction here with the two reactions we have? So you have to kind of look at what you are given and how you can get there. For instance, if I looked at the reaction I have NH3 on the left, and I don't see NH3 anywhere else, but in the reaction I want, it's on the right. So what am I going to have to do? And there's 4 of them. So what I'm going to have to do is I'm going to have to take this reaction, reverse it, and multiply it by 4. So what will that look like? I'm going to write it down here. So if I reverse it, 1/2 times 4 is 2, N2, plus 3/2 times 4 is 6, H2 yields 4 NH3. And I know that this is not the lowest ratio, but that's not the issue right now. Right now I need to have 4 NH3s to get to my reaction here. And my delta H is going to be 4 times the one given, which is 184, but we also reversed it. So that is definitely true of all reactions. So this reaction right here is endothermic. Okay, 46 kilojoules is going in to make this break apart and these to form. And with these mole ratios of 1, 1/2, 3/2, that is the amount. Well, if I reverse that reaction, instead of being endothermic, it will be exothermic, as we see here. That's what I'm doing here. I want to try and separate these a little bit better so I can see what I'm doing, because I'm going to add two reactions together here. So then I need to look at my other equation and think about what's involved here. It looks like water, only place we see water, and here is water also in this reaction. What about nitrogen? Oh, nitrogen we already took care of from the first one that we did. I didn't actually watch that, but it'll always work out. Everything that's given to you will work out as far as things canceling and forming. You just need to decide, do I have to reverse it? Do I have to multiply it by anything to get what I want? So here's what I mean by that. This is the only place we see water, and there's two of them. And in a reaction, here it's on the product side. In a reaction here that I want to get to, it's on the reactant side. There's 6 of them. So I'm going to take this reaction that I see down here that I'm given and multiply it by 3 to get to the 6. But also, I'm going to have to reverse the sign. So let's just multiply by 3 first. So my reactant now would be 6H2O, and that's going to yield 6H2 plus 3O2. The delta H is going to be 3 times the 484. 3 times 484 is 1452 kilojoules, and now it will stay positive. I don't need to write that, but I could, but it will stay positive. Now I need to add those two reactions together just to make sure that it gets me back to my original here. So I have 6H2, actually I'll just try to keep it written the same way. 2N2, looks like my 6H2 are canceling out, so essentially whatever I started or used up formed more, so that's the way you can think of it. It cancels each other out, so it wouldn't be part of the final reaction. Plus 6H2O, that yields the 3O2 that you see here, plus 4NH3. So what would be the delta H of that reaction based on these numbers? I'm going to take that 1452 minus 184, and that would give me a total delta H, I don't know why I didn't put an H there, of positive 1268 kilojoules. So that's what you need to do for your the practice worksheet. There's a key also there, but you need to look at the equations given, decide if you need to reverse them or keep them in the same direction that the reactions are written, decide if you need to multiply them by any number. It could be cut in half. Here we didn't do that, but you could cut it in half, which just means that the delta H would be cut in half also. So you need to think about what you have to multiply them by to get to that final reaction in the end. So this is the goal of the reaction. You're using reactions that you have a delta H for and manipulating them in a way that you can add the reactions given to get the reaction that you're looking for in the end.